Hello, welcome to this short video where we just go back over some of the assumption checking. I have talked about this a little bit in the video where I produced the output, but just to kind of reiterate. So the first part of the file that we have, if we imagine this is all we had to go on, we can see that we've got information on the number of cases we've got. This is the kind of we've used the explore function in SPSS to produce some descriptive statistics, some tests of normality, and to also produce some plots that can help us to understand what's going on with the data. So typically what we might start off with doing is looking at the case processing summary, and we look at whether this is the number of participants in each of our groups, so in this case males and females. Is that what we had anticipated? Do we have any missing data that we've got to be aware of that would impact on how we have to think about how we handle missing data when we're doing things like ANOVA and MANOVA and regression. So we can see here that luckily we have no missing data. We've got roughly equal numbers of males and females, and that is what we were expecting, 90 males and 88 females. So the next piece of information I would look at is to try and understand how the data on materialistic aspiration mean scores, how that's distributed for males and females, and then the same for the non-materialistic aspiration attainment score. This is the traditional way of testing the data assumptions. So this is where we look at each level of our IV, we look at the distribution of our dependent variable, and that's what the assumption of normality is, that at each level of our independent variable or variables, our outcome variable will be normally distributed, or rather roughly normally distributed. So I'll contrast this with the kind of more new contemporary ways of looking at this, which are particularly useful if you've got quite complex data, if you've got, or rather you've got large numbers of independent variables. Actually breaking it down, if you're being really thorough, what you should do is break it down by each group, each subgroup, and so on. And if you've got lots of independent variables, then doing that for every combination of levels of your IVs can become very time consuming and very challenging actually to interpret. So the kind of more modern approaches that are emerging for checking normality, we'll look at in a little bit. And actually, if you've got multiple independent variables, it's probably more streamlined than the traditional approach. So the first thing I would look at is the mean for the group, and I might compare that to the trim mean. So the trim mean is where you chop off the ends of the distribution. So if you've got really heavy skew or you've got really extreme scores, what you'll notice is a big jump between the mean and the trim mean. In this case, we can see they're very similar to each other, so that's a good sign. One of the issues is that there isn't a cutoff, a difference score then, where the difference between the mean and the trimmed mean becomes important. It's basically knowing the context of the variable. So if I saw, knowing that this can only vary between, on a mean score, if I saw a big jump from 2.8 to, 0.05 here, that would be a big problem, knowing the range of potential scores on this outcome measure. But in this case, we can see they're very similar to each other, so that's a good sign. Also, if you had a perfectly normal distribution, your mean and your median would be identical. But the closer they are together, the more normal the distribution. So again, we can see a bit of a change, but not too much for this variable. And we can see that our skew and kurtosis values are within -1 to +1. Now that's a really good sign. That suggests that even if we do have a non-normal distribution, that actually individually these things aren't too worrying. So we might have not a perfectly normal distribution, but a roughly normal distribution. But we would do a little bit more checking with that as well. So kurtosis refers to how pointy or flat the distribution is. If you have a negative value for kurtosis, you have a flatter than normal distribution. If you have a positive value, then it's pointier than a normal distribution. If it's 0, you've got absolutely no problem. And skewness, if you've got a positive value, then you have a positive skew, which is also called right-handed skew. So the tail of your distribution is to the right-hand side of the graph. If you've got a negative value here, then you've got negative skew, or also called left-sided skew. So the tail of the distribution is to the left of the graph. So we have some positive skew, and we have a slightly flatter than normal distribution based on this. And so we need to do that just to sort of eyeball the data for each of these subsets. So for females on materialistic, for males on non-materialistic, and females on non-materialistic. If we just scroll through, the one that seems a little bit less normal than the others based on this looks like males in the non-materialistic mean score variable. That's approaching kind of -1, so it's starting to become more extreme. But we can double check this as we go along with things like our test normality and our histograms and box plots as well. When you're choosing between your test of normality, either the KS or the Shapiro-Wilk, you should use the Shapiro-Wilk when you have less than 50 observations. In this case, we've got more than 50, so we can use the Kolmogorov or Smirnov test. If in doubt, probably just use the Shapiro-Wilk. But what we can see is then that they are telling us slightly different things. If we go with the Shapiro-Wilk, then for the first variable, both of these look kind of borderline. They look roughly normal based on just the significance. So if that value is greater than 0.05, then we don't. Our distribution is not significantly different from a normal distribution. What this is just telling us is that our data for these variables is kind of on the borderline. And this one here, for this one, the one that we eyeballed using the skew and kurtosis values, this looks more pronounced. Okay, so this is definitely not significantly different from, a normal distribution. But at this point, we don't know how much different. It could just be a small amount, or it could be really substantial. One of the issues is that with either test, as soon as you're approaching sample sizes of 100, these tests will become incredibly sensitive. So you should never base your decision purely on your tests of normality. When you have slightly larger sample sizes, which we do, you need to take make a decision in combination with this and your descriptive statistics and your graphs and things. So we'll go on and have a look. Okay, so we've got something that doesn't look brilliantly normal, but actually on balance we know that it's got roughly normal skew, roughly normal. It does look slightly flatter than a normal distribution. We ideally would want nice sloping, gradually sloping sides. We don't have that, but again, I would look at that and think, okay, based on my sample size, that's not too concerning. Same for this one. We've definitely got more skew, but it's not too pronounced. And our QQ plots, again, they're suggesting they're not perfectly normal. If these, if this was perfectly normal, each of these dots would be sitting on the line exactly. We can see it's following the trend, but it's not quite there. I always ignore these ones. I think they're hard work to interpret. And then, so we'll look at our box plot before we move on to the non-materialistic scores. So our box plots look at slightly different information. So they have the median here. This is the interquartile range in the box. So that's where the majority of our scores will end up. And this is the highest non-extreme score and the lowest non-extreme score. If this is a perfectly normal distribution, this box here, the line would be in the exact middle of it. And these two whiskers would be identical in length. So we can tell from there we've got a bit of skew, there's something going on, but we already know that from our histogram. The main reason you'd use your box plot is to try and identify if you have any really extreme values. SPSS shows you extreme values in two different ways. One is a circle, and that's the actual row number in your data set. So that's row 156. And we can tell from there that that's a mild outlier. So it's It tends not to be too concerning if they're a mild outlier. If we have any problems later down the line with our analysis, that's something you might want to investigate further. The issue would be if you've got an asterisk, then that would be a really extreme score. I think it's something like 3 times the interquartile range. So it's really quite different. And you'd probably want to explore that further. Check what the score is in the row that's been identified. See if it's perhaps a data entry issue. You can also follow that up by getting SPSS rather, to calculate the Z-scores for each case and see if you have any scores of 3 or -3 or more. That would be a really, really extreme score. So that's a slightly different way of investigating outliers. In this case, I'd say that a mild outlier, it's not too concerning, so we'll leave it in for now. Okay, so here we get the variable which isn't normally distributed. And we can see that there is quite pronounced skew really here. We've got a longer tail to the side, but we know actually we've got a reasonable sample size and that our skew value, even though it's more pronounced, was still within -1 and +1. So, you know, and again, this one's skewed as well. So we've got some decision making we'll have to do around that. And one of the things is that there are different approaches to handling this. One might be to try and transform the data now to see if it improves the situation. So things like a log transformation or a square root transformation. If you want to learn about those, there are some really good guidance in Andy Field's textbook, Discovering Statistics Using SPSS. And he talks through when you might use different types of transformations. So some are better for dealing with negative skew, which is the thing we've got, and you might want to try those. More often than not, a transformation fixes some problems and breaks others, causes other problems, and also it can make the interpretation of your data after your analysis really challenging. So that might not be, that's an approach you can take, but it might not be the best fit. An alternative might be, if you're really worried about this, to say, okay, I'm going to not do the mixed methods ANOVA, I'm going to break down each of the effects and look at them using non-parametric tests instead. Unfortunately, there isn't a direct equivalent of the a non-parametric mixed methods ANOVA. So what you should have to do is break down and analyse the variables separately and then do a test of simple effects to explore the interaction effect, which is one of the things we're interested in for our hypothesis. So that would be an alternative, and I've had to do that in some research that I've done as well. The other approach is to argue, actually, because of our sample size, that the ANOVA should be fairly robust to these issues. So, for example, Tabachnik and Fiddle argue that if you've got at least 20 observation in the smallest cell, that things like ANOVA and MANOVA should be fairly robust to moderate violations of the assumption of normality, which is what we've got here, basically. So you could go down that route and argue that you check this, but because of sample sizes, actually you think that the analysis will be fairly robust. Another way you might want to check this is actually to use a slightly different way of checking these. As I said, this is the traditional approach to assumption checking. So what we could do is to explore normality using the residuals in our data analysis rather than the raw data. And the reason we can do that is that it would allow us, rather than breaking everything down by group, we can actually just look at the residuals on their own, and that's because each residual is calculated based on some information about your independent variables. So it is actually still exploring the same assumption in the same way, but it may be a more convenient way of doing it, and it may show us a different pattern. And there's a paper on Blackboard which talks you through the benefits of using that approach with ANOVA. And essentially, it's actually exactly the same way that we check the assumptions in regression. So there is a convention for doing this, but it depends whether you want to go with the traditional or the more contemporary approach. So if I scroll down, we did this, And so we've got here a studentized residual. You could use your standardized residual. They're calculated in slightly different ways, and the reason for using a studentized residual is that it can help you to identify, because of the way it's calculated, it can help you to identify extreme scores more easily than just using a standardized residual. But if you have a look at Andy Field's book, he talks through the difference between standardized and studentized residuals if you want to learn a bit more about that. So we've used the studentized residual, and you can see actually what we've done is we've calculated that for the materialistic attainment variable in our data set and the non-materialistic attainment variable in our data set. And rather than breaking it down by each subgroup, what we've got, or gender in this case, what we've got is we're looking at the data for all 178 cases in one go. Because it's a form of standardized variable, the mean statistic is 0. What we can see here is we've got skew and kurtosis values again within -1 and +1, so that's a good sign. And again here within -1 and +1, but this is less normal again. Because we've got a large sample size, we should basically just take the test results for the test of normality with a pinch of salt. This really doesn't tell us much. But if we plot out our residuals, what we can see again, it's not perfectly normal. We've got a moderate violation, I'd say, of the assumption of normality here. It's roughly normal. This variable is quite obviously not perfectly normal. Again, this one's more pronounced. Again, we have to make the same decisions then. Are we going to use this? I'd say this is definitely a moderate to more substantial violation of normality. But it's not too extreme. So again, we can make the argument based on sample size that we're going to proceed with the ANOVA, or you may want to try a transformation and see if this improves the situation. Rerun the assumption checking. If it doesn't, then you've got a reason, I think, to stick with the raw data. Or you could now break it down and, as we've said earlier, look at these things using a non-parametric series of tests. But those are kind of mainly around the assumption of normality. There are some assumptions within the actual ANOVA itself that we need to look at, and one of those is if we go to the actual results of the Mixed Methods ANOVA. The first one's the boxes test. If that value is less than 0.001, we have a problem. It's on 001, so this is legendarily sensitive. If you've got equal numbers of people in each group, then you can ignore it, and we've got roughly equal numbers, so that shouldn't be much of a concern even if we had violated the assumption. If you want to learn more about what that is, have a look at Andy Field's book, or have a look at Julie Pallant's book. She talks about that as well. So the first thing that we want to look at, you might look at this and think, okay, I remember from looking at other lectures that sphericity is important, but hang on a minute, there's no value in there. What does that mean? Have I done something wrong? No. Mauchly's test, or Mauchly's test, only comes into play if you've got a repeated measures element with more than 2 levels. We have got a repeated measures element, goal type, so people rated attainment based on non-materialistic goals and then materialistic goals. But we've only got 2 levels, so that's why it hasn't been calculated. It's not relevant here, so we can ignore that. What it means is when we when we choose which row of test statistics here to interpret, then within the tests of within a subject's effect, we can use the sphericity assumed goal statistics for goal type and for goal type and the gender interaction term there. The next piece of information we need to look at are the Levine's test of equality of error variances. This is similar to the homogeneity of variance test in a t-test. So we're interested in looking at this based on the mean, so we can ignore this. What happens is that if this is statistically significant, so the value in the p-value column here is less than 0.05, then the error spread outness for our 2 groups is different, which can arbitrarily produce an effect. It might look like our means are different, but actually it's not. It's just because the range of scores within the 2 groups differ. So we have to check for this. In the first variable, we don't have an issue, that's greater than 0.05. In the second variable, we do. And so this can be a tricky one to resolve. It might be worth, again, looking at those transformations. The alternative is when you're analysing the results of your between groups main effect and the interaction term, is to drop your p-value, your usual cutoff, from 0.05 up to 0.01. So when we're interpreting this, we would interpret it rather than against a p-value of 0.05, we would interpret it against a p-value of 0.01. And when we are interpreting the test of between subjects effects, in particular gender, we would evaluate that against a new p-value of 0.01 rather than 0.05. So it can be the difference between identifying a significant effect or not. But the reason that we do this is to try and curtail the error that creeps in because we violated that assumption. Okay, so it's something you would have to be aware of. For more information, again, look at Julie Pallant's book and look at Andy Field's books. They talk about different approaches and to handling this. So those are the main assumptions for the Mixed Methods ANOVA. So have another look at that and see if you have any questions. Don't forget you have your lecture on ANOVA that talks through some of these things as well. Then pause this video and now have another look at your the actual results of the ANOVA, which we'll go through next.